Welcome everybody to the seminar on computational geometry and robotics. When the speaker will start, you can unmute yourself if you wish to ask a question or write it down in the chat and I'll occasionally read it. We are very happy to have as our speaker today, Esther Ezra from Bar-Ilan University. Esther is no stranger to this seminar. She's actually a frequent speaker in the seminar. It's also where Esther studied. So let me just introduce the title, Ray Shooting Amid Triangles in 3 Dimensions. Esther, please.
Okay, thank you, Danny. So this is a joint work with Micha Sharir, and I'll define the problem first. So we are given a collection T of n triangles in 3 space, and the triangles are given in an arbitrary position. They can intersect. And the ray shooting problem is to preprocess T into a data structure such that given a query ray, we can efficiently report the first triangle that the ray hits. If such a triangle exists, it may the ray may go to infinity. This problem is a very well-studied problem in computational geometry. It arises in ray tracing, in hidden surface removal, in other problems related to computer graphics. But it also has applications to hardcore problems in computational geometry. And I have several examples to such problems. So here is one of them. Intersection reporting or emptiness amid triangles in 3 space. So here we are given a set of triangles in 3 space as before, and you would like to pre-process them into a data structure that supports a line, ray, or segment emptiness or reporting. What does it mean? Given, say, a segment query, you would like to decide whether it intersects any of the triangles. This is called emptiness. Or alternatively, you would like to report the subset of the triangles that it intersects. And in this case, we also require that the query time will be output sensitive. Okay, so usually the query time is a small overhead term plus the output size. All right. Another problem is called intersections among lines in 3 space. So this is just a 3-dimensional illustration. Here we are given a set of lines in 3 space, and we would like to either detect, count, or report all pairwise intersections. Okay.
Esther, will you tell us, are you going to use your tools to solve the line intersection problem, or you're just mentioning it as a relative?
If I have time, I will explain that. But in principle, what you want to do, if you think about the bichromatic question, say you are given a set of red lines and a set of blue lines, and you would like to know whether there is any red-blue intersection. So once you are given a ray-shooting machinery, you can pretend that, say, the red lines are the triangles, they are the degenerate triangles, but you can still preprocess them within the same data structure. It's even simpler in this case. And then you use the blue lines as the query rays, and you just shoot.
Okay.
Yes. Okay. Another 2 useful applications are for computing the intersection of 2 non-convex polyhedra. So we are given a red and a blue non-convex polyhedra in 3 space, and you would like to efficiently compute their intersection. Now, the complexity of their intersection might be quadratic. So this is a 2-dimensional cross-section of 2 such polyhedra. So what you can do is to sweep this picture along the z-axis, and what you obtain is 2 polyhedra whose intersection complexity is order of n square. So here too, what is common to do is to use, say, every polyhedra is given as a triangulate. All the faces are given as triangles, say, of the red polyhedron. And so we process them to array shooting machinery, and then we array with the edges of the blue polyhedron. And another problem is for arrangement construction of triangles. So we are given a set of triangles in free space, and we would like to efficiently construct their arrangement. What does it mean efficiently? So in brute force, it is very easy to construct three-dimensional arrangements in time that is n cubed, where n is the number of objects. So here, this is not the amount that we wish to pay, because if the arrangement is sparse, we would like the cost to be much smaller. So, in output sensitive construction means that the time consists of a small overhead term plus the arrangement complexity. Okay.
Esther, excuse me for bursting again. Can you tell me what is your overhead term for the arrangement construction?
Yes, I will say it, but I can also say it right now. It's n to the 3/2. All the overhead terms, also in these questions, are n to the 3/2. So here
and
the time.
Rest is the complexity of the arrangement?
The rest is the complexity of the arrangement. It's n to the 3/2 plus k log of k.
Okay.
Because again, what you do, you process the triangles to ray shooting, and then you shoot with the edges of the triangles, and then you get all pairwise intersection, and then on every triangle, you can use, say, two-dimensional sweep line, right? And
yeah.
This is output sensitive. But I will revisit these questions, these problems, with the new bounds and the previous bounds.
Okay.
Okay. So, so previous work about ray shooting. So this is before the discussion about the applications. So this is, again, a very well-studied problem. There was a lot of activities during the 90s. And I was looking at the Pankaj Agarwal-Survi paper. I am going to state bounds that are taken from a table in his paper about ray shooting among different settings in different dimensions. Okay, so first in the plan, with simple polygon. So for ray shooting in a simple polygon, there are data structures of overall linear complexity and query time logarithmic, log of n. Now for segments in the plan, there is what is called trade-off bound, meaning that if we are willing to pay, say, order of m for the storage, then the query time will be n over m to the 1/2. So the storage parameter m is an integer parameter between roughly n and n squared. And when m is equal n to the 2 plus epsilon, the query time is polylogarithmic. And when m is linear, the query time is roughly root of n. So this is the meaning of trade-off. The more we are willing to pay for the storage and pre-processing, the less we pay for the query. Okay, and so this is very common in research. Other settings are for disjoint arcs in the plan. So here it is known with linear storage, the query time is the root of n. What is the situation in 3 dimensions? So ray shooting for convex polytope, with the hierarchical decomposition of Dobkin and Kirkpatrick, this can be done in overall storage linear and query time logarithmic. For plane or half planes in 3 dimensions, here there is also a trade-off bound, m and n over m to the 1/3. This was given by Agarwal and Matushak in 93. I will give some details about this work shortly. And the case of triangles, this is the case that we focus on this presentation. The trade-off bound is m and n over m to the 1/4, where m runs roughly between n and n to the 4th. So when m is equal to m to the 4 plus epsilon, the query time is logarithmic. When m is roughly linear, the query time is n to the 3/4. Okay, so this is where we are putting our finger in this presentation. And for higher dimensions, Agarwal and Matushak showed a trade-off bound for hyperplanes. This is the bound. And they also showed a bound for ray shooting in a convex polytope. So this is extending the bound of Dobkin and Kirkpatrick. Okay, so a couple of comments about the previous work. So the work of Agarwal and Matushak, that was one of the significant work at that time, which actually showed a reduction from ray shooting to segment emptiness. And they did that by a parametric search mechanism. What does it mean? It means that if you give me a data structure for segment emptiness, then with only a polylogarithmic term, we can construct a data structure for ray shooting. So segment emptiness, I discussed that problem before, but let me just give you the full detail how it is defined. So this problem is part of the whole family of range searching, and it is part of a subfamily in range searching that is called intersection searching problem. And it is defined as follows. We are given a set gamma of geometric objects, arcs or triangles, free space or whatever, and if we pre-process them into a data structure, so that given a query segment S, we can efficiently decide whether it intersects any object. Okay, so either it intersects an object of gamma or either it does not. So like I said, once we have an efficient segment emptiness mechanism, we obtain ray shooting mechanism with similar performance up to a polylogarithmic factor, because this is the overhead of parametric search. Okay, so this is one comment. Another comment about the case of triangles in free space. So like I said before, the trade-off bound was M for the storage and N over M to the 1/4 for the query. And this is because the problem at that time was lifted to 4 dimensions. And all previous work actually suffer from the curse of 4-dimensionality of line in free space. What does it mean? A line in free space can be parameterized by 4 parameters. Say if you take the 2 planes z equals 0 and z equals 1, you collect overall 4 coordinates and they comprise the parametric representation of the line. So, so we can actually map the problem to R4 by mapping the triangle edges to surfaces in R4 and the query ray to points. So without getting into too many details, the conditions that a line intersects a triangle can be expressed as a semi-algebraic set in R4. Okay, and so we actually collect them, and what we obtain is an instance of a range searching problem in R4 for points and semi-algebraic sets. And even just a comment in even more earlier works, this problem was mapped to a 5-dimensional Plucker space where the relevant object lied in a 4D surface, the Klein quadric. But yeah, this is just for just saying a couple of words about the history. But overall, what this mapping did is to map the problem to a range searching problem of points and surfaces, semi-algebraic regions in R4. And this eventually led to the trade-off bound of M and N to the M to the quarter, okay, on storage and query time. Now in our work, okay, before discussing our work, just one more thing, this slide. So, so a wishful thinking is that since triangle and free space are flat, then we may hope that the ray shooting among triangles would behave like ray shooting among planes in free space. So for planes, we do have the trade-off bound M and N over M to the 1/3. So this is the goal, or this is the wishful thinking, obtaining this bound. We don't know if this is realistic, if this bound is actually the true bound for all values of M. But this is one thing that we would hope to get. Still, so we don't have a complete answer on this question, But what we managed to show is such a bound for a specific value of m, okay? And this is our result. So our main result in our mechanism, we apply a pedestrian approach in 3 space. What does it mean? We don't lift the problem to 4 dimensions, we stay in 3 dimensions. And we apply the search there. So our main theorem is the following. Given a collection of n triangles in 3 space, they are arbitrary triangles. They can be intersecting triangles in particular, and a prescribed parameter epsilon. We can process the triangles into a data structure whose overall complexity and pre-processing time is n to the 3/2 plus epsilon, so that array shooting amid these triangles can be answered in n to the 1/2 plus epsilon time. Okay, so where is the improvement? So for the choice of m equals to n to the 3/2, the previous trade-off bound gave query time of n to the 5/8. And we improve it to roughly root of n. Okay, so this is the improvement. And now I'm going to revisit those applications and state the new bounds. All right, so for intersection, segment
you also generalize it, sorry, Esther, you also generalize it to higher dimensions, or it's just in 3D?
We didn't. I suspect this can be, well, again, without checking too much, I suspect this can be generalized to simplices in 4 dimensions. At least the machinery that we use, it may support it, but we don't have such a generalization. We didn't work on it, but I will not be surprised if this is the case. So one of the open questions is not exactly about high dimension, but about different objects like curved objects, balls or hemispheres. With this, we don't know how to handle, at least not at the moment. Okay, so one theorem about reporting or emptiness amid triangles in 3 space. So we're given collection of n triangles and a parameter epsilon, and we can process the triangle into a data structure of size n to the 3/2 plus epsilon, so that segment intersection, emptiness, or reporting query can be answered in time n to the 1/2 plus epsilon. Okay, so we know how to conduct emptiness or reporting. On the other hand, the ingredient that is missing is segment intersection counting. We don't know how to answer with the same asymptotic time bound segment intersection counting. That is, given a segment, how many triangles does it intersect? Currently, our machinery does not support it. And this is in contrary with the previous work, the one that did the lift into 4 dimensions. There, the same bound also holds for segment intersection counting. So this is one gap that our work leaves. We currently cannot tell whether this is doable or whether there is a reason, that is, whether there is an actual lower bound that is hidden here. Yeah, I think it's a very interesting question to understand this gap. And another application, the one that I discussed before, detecting, counting, or reporting line intersection in 3 space. So like I said, we consider the bichromatic version. We have a set R of n red line, a set B of n blue lines, and detecting whether there is a red-blue intersection cost n to the 3/2 plus epsilon. What about?
So Esther, what was the previous best bound for that?
The previous bound? So as a matter of fact, I don't know. I mean, there are other questions that went around this. As far as I know, Pellegrini studied several questions, but not this particular one. So I don't know if there was, obviously that was easy to do with n to the 8/5 plus epsilon using the same machinery. But for this particular problem, I don't know if that was even considered.
Okay.
On the other hand, these 2 problems were considered by Pellegrini, computing the intersection of 2 non-convex polyhedra. So we have an algorithm whose running time is n to the 3 half plus k log k, and the previous bound was n to the 8 fifths plus k log k. The same thing goes with output sensitive construction for triangles of triangle arrangements. The running time is n to the 3 half plus k log k, and Pellegrini gave n to the 8 fifths plus k log k.
I still want to discuss this, if it's okay with you that I interrupt you.
This.
Yes.
Sure.
What are you computing? Because, for example, I guess you are computing the map over each triangle. But how do you describe the three-dimensional space, the cells in space and their relation?
So you compute the arrangement over each triangle with sweep line, and then you can use, say, cross pointers between the features. I think this is pretty standard.
No, so Esther, let me clarify. Within
Yes.
each connected component of the triangles, obviously you can move from anything to anything by using the standard machinery. But now I'm telling you that inside one of your three-dimensional cells of the arrangement, there are a few floating other components of triangles, but they are, how do you know the connection between everything?
How do I know the connection?
Once you're on one,
how do you know?
Component, it's obvious.
I see. How do you know? In which connected component it is contained?
Yes. How do you describe the three-dimensional components of
I see what you are saying. Yes, actually, I don't know. We didn't think about it, and it may be a missing ingredient. We just yes.
So I just want to make a comment.
Yes.
You really obtain a better bound than what was known before, but what is known before for computing three-dimensional arrangement triangles as quadratic overhead, but it really gives you a full description of the three-dimensional decomposition.
Yes, true. And this one only gives you, so this is not a decomposition. This is just only the elements of the arrangement.
Yeah.
Yes. Computing vertical decomposition is a much more difficult task.
Yeah, we know how to do it with only quadratic overhead.
Exactly. Yes.
Still efficiently, but it requires quadratic overhead.
Exactly, and it is also quadratic in the worst case if you have two sets of triangles whose projection creates a grid. Yes. I don't believe that. I mean, computing the vertical decomposition must be more difficult and should take more time, but this is not what we are computing. These are only the elements of the full arrangement. Yes. Okay. All right, and the next thing is the trade-off bound. So we got the somewhat bizarre trade-off bounds because we have only one value of S where we got an improvement, whereas the rest of the values, I mean, in the trade-off, the all trade-off bounds are just remain the same. We did not improve them. So if we combine our new machinery with the previous trade-off bound, the S and N over S to the 1/4, we get these query times. We have a break, and here we have a breakpoint for when the complexity S is below or above N to the 3/2 plus epsilon. Okay, and this is actually a schematic figure of our trade-off bound. So the green line represents the all trade-off bounds, the S and N over S to the 1/4. This scale, by the way, these are logarithmic scale of the storage complexity. So this means N to the 4, and the query complexity, this means N to the 3/2. So when S is linear, we get N to the 3/4 for the query time. When S is N to the 4, we get logarithmic. But as we get closer and closer to the point of N to the 3/2, we improve the running time of the query time. Okay, so this is the new trade-off, the red curve, the red polygonal line. Okay. So far I just presented some background and our new result, and now I'm going to tell you what tools we are using, and if I have time I will tell you about our technique as well. So the main tool in our arsenal is the polynomial partitioning by Guth and Katz, and later by Larry Guth. So this is, so to speak, a geometric divide and conquer mechanism for any set of algebraic, for any collection of algebraic sets in RD. So in our problem, the collection S of semi-algebraic sets are lined in three spaces. As a matter of fact, they are the lines that contain the edges of the input triangles. And what is the goal in such a mechanism is to obtain the composition of space into open simply shaped cells so that each of the cells meets only a small fraction of the object in S. And therefore, this is indeed a divide and conquer. Every cell is its own, it's a subproblem by its own. Then so far, polynomial partitioning have mainly appeared in incidence problems in discrete geometry and the relatives problems, but there are also very few applications in more algorithmic questions like range search and point location. And in this work, we show another application of polynomial partitioning for way shooting. Okay, so I will demonstrate to you the notion of polynomial partitioning. First, I will just demonstrate the notion for the concept for points. We do not use polynomial partitioning for points. It is only helping to understand the general idea. Okay, so this is a theorem by Guth and Katz, and they showed that for a set P of n points in RD and a real parameter capital D, which is the degree of the polynomial, there exists a polynomial f of degree D whose zero set z of f, zero set, these are all points in space such that the value of the polynomial is 0. So the zero set partitions P into D to the D sets, with and each of them contains at most n over capital D to the D points of the input P. And each of these sets lies in a distinct connected component of the complement of the zero set. This is what we refer to as cells. Okay, so I will show you an illustration of polynomial partitioning. Let me just comment that a typical issue in this partitioning is how to handle the points on the zero set, because in principle there is no restriction on how many points can fall into the zero set, and in particular all the points can fall there, and then each problem has to handle the zero set in its own way. Okay, so here is a two-dimensional illustration for polynomial partitioning. The red dots are the input points P. The black curve is the zero set of the partitioning polynomial f. So like you see, it intersects itself in many points. These points of intersection are also referred to as points of singularity. And the zero set forms a partitioning of the plane into cells. So the polynomial partitioning theorem of Guth and Katz tells us that in each of these cells, there are at most n to the d, in this case, d squared, because we are in the plane points. Some points may lie on the zero set. And this blue line here, this is a preparation for the next slide. So a line intersects the zero set in at most capital D points. And why is that? Because we can take the parametric representation of the line and substitute it within the equation of f, and then you get a univariate polynomial of degree at most d. It has at most d roots, and each of these roots is exactly an intersection point. Okay, so this is points. That was just an introduction, but what we need in our work is polynomial partitioning for lines in free space. And this is a slightly later theorem by Larry Guth. This is actually a much more general theorem, but I state it only for lines in free space. And it goes as follows. Given a set, a finite set L of n lines in free space and a parameter d, there exists a triviate polynomial f of degree at most d, whose zero set z of f partitions free space into d cube open cells. each of which is intersected by at most n over d square lines. Okay, so now the factor, the right factor is n over d square. For points, the factor is n over d cube. And why is it the right factor? Let us just make a quick checkup. So like I said before, a line of L meets the zero set in at most d points. So the overall number of intersection lines versus z of f is n times d. On the other hand, the number of cells, the number of connected component in the complement of the zero set is roughly d cube. Let us assume it is d cube. It can be less, but just for the sake of this illustration. So on average, every cell gets n over d square lines. So this is the best possible bound. I mean, this is the bound on average, but with a lot of effort, Larry Good managed to show that there are polynomial partitioning for which this is the bound in the worst case. Okay, and here too, we also suffer from the problem of the zero set because it may happen that many lines will eventually lie on the zero set and you need to handle them using a different approach. So here are two examples for doubly ruled surfaces in 3 dimensions where they actually consist of lines. So say if this is the form of the input line, it is very likely that the polynomial partitioning will be one of these doubly ruled surfaces, and then we need to handle them over these surfaces. Okay, and what about the algorithmic versions of polynomial partitioning? So there is a recent work of mine with Agarwal, Aronov, and Zal, where we showed that the theorem of Larry Good is constructive or can be made constructive. What does it mean? For the case of lines, we are given a set of L of n lines in R3 and a parameter D. So a polynomial partition in F of degree at most D can be computed in this expected running time n. Poly D means polynomial factor of D plus e to the power of poly D. This is an exponential factor. But if we choose D to be a constant degree or large constant degree, then the expected running time is only linear. Is only order of n. And this is what we need for our problem. So in our ray shooting problem, the pedestrian approach is to construct a polynomial partition in F for the 3n line that contains the edges of the input triangles. This is how we start. Okay, so we actually make a recursive construction. This is a divide and conquer mechanism. We construct a polynomial partition in F for the 3n lines. These are the edges of the input triangles. I'm going to explain this, this step in much more detail shortly. Okay, now it's time to turn on the light. The query ray row. So there are two cases. Either the query ray is not contained in the zero set, and then it means that we need to walk along the cells of the partition that meet row. And in each of them, we need to solve the ray shooting problem recursively. I'm going to explain that in more detail shortly. And we collect all kinds of answers, and we need to return the hitting point that is closest to the origin of row, if such a point exists. And if the query row lies in the zero set, then we need to apply a ray shooting procedure within the zero set. So this is a different mechanism. This eventually boils down to a two-dimensional ray shooting problem, which we also had to build a structure of its own. So I will explain that in slightly more detail. So now for the recursive construction. So D, capital D, like I said, this is the degree bound, which we take to be a constant. And we construct an expected order of n time a polynomial partition in F for the 3n edges of the input triangles in T. So these partitions R3, the three-dimensional space into d cube open cells, each of which intersects at most n over d square triangle edges. Okay, so this is the ratio that we get. This is a good ratio. With this ratio, we will eventually end up with the n to the 3 half bounds. I will show that when we get to the recursion. But just for continuing my description, we classify the triangles with respect to every cell tau. That is, we are given a cell of the partitioning tau. This is an example for such a cell. They are semi-algebraic set that they can have all kind of shape, a torus or any other nice shapes that you can imagine. So we are given a cell tau of the partition and a triangle delta. So we call the triangle delta narrow in tau if delta has an edge that crosses tau. Otherwise, if it does not have such an edge, then we call delta wide. So this illustration is for the wide case. This triangle does not have any edge crossing the blue cell. Okay, so using the bound on the number of edges that cross a cell tau, we can conclude that the number of narrow triangles in tau is only n to the d square because we can charge them to the edges. That means that these triangles are scarce and we are going to handle them recursively. Okay, on the other hand, the wide triangles are more popular and we need to have a separate mechanism to handle them and dispose of them immediately. That is, we are not going to process them in this recursion. And one of the wrong intuitions that has to be referred, has to be stated, is that at first sight, it may look like that a wide triangle, that is a triangle with no edges crossing the cell tau, may behave like a plane. That is, we can actually extend the triangle to a plane and then say that this plane represents locally the triangle inside the cell. But this intuition is wrong, and this is the picture that demonstrates why is it wrong. This is a two-dimensional cross-section. So this is the triangle, okay? Now, if we extend it to a plane, then we actually also get the dashed line. And then a ray shooting inside the cell, if we make this extension, we will end up with a false answer. So we cannot make this extension to planes. We need to do something else. But if we had such a property, that would be great, because if wide triangles behave like planes, we could just use the on-the-shelf ray shooting machinery for planes in free space and resort to the trade-off bound of m and n over m to the 1/3 for ray shooting, and that would be more or less it. But it is not that simple. And we actually had to work very hard to handle wide triangles. So I prepared a few slides at the very end of the talk. If I have time, I will explain that. But what we managed to show in this non-trivial step of the analysis is that for a set W of n wide triangles in a cell tau, we can construct a data structure of size and pre-processing time of n to the 3/2 plus epsilon, so that ray shooting query within tau can be answered in n to the 1/2 plus epsilon time. That is, this eventually gives us the bound that you would want to get from by replacing the triangles with planes. It's just that we had to use several tricks to get there. Okay, so this is what we get for wide. What about the zero set? So if we have the ray row, it completely lies in the zero set, like the W ruled surfaces that I demonstrated before. This was one example. Then we need to build a ray shooting mechanism within the zero set. Okay, So what do? We take a triangle delta. This triangle delta intersects the 0 set in an algebraic curve of degree d because the polynomial f is of degree d. So this is an illustration for one cell. This is a torus, and the black curves, these are the cross curves, the intersection curve of a triangle and a cell tau. Okay, so here we need to apply a decomposition of the 0 set into XY monotone patches. This can be done by the so-called cylindrical algebraic decomposition. It's a separate machinery. And then we can project every piece to the XY plane. And what we get is a collection of algebraic curves on the XY plane. And this eventually boils down to the question of ray shooting amid algebraic curves in the plane. Okay, this is the problems that we faced with. And here again, we had to develop a new machinery. It's not that there were not other machineries from previous work. It's just that we did not find a machinery that gives the bounds that we need. So there was, for example, a previous work by Vlad and Colton who showed that with the roughly quadratic preprocessing, one can answer a query, a ray shooting query within logarithmic time. But what we needed to get are the bounds of n to the 3/2 and n to the 1/2. So we showed in a separate development that given a collection of constant degree algebraic arcs in the plane, we can construct a data structure of size and preprocessing cost n to the 3/2 that supports ray shooting query in time n to the 1/2 plus epsilon. And even moreover, we can do better when we replace the ray by a line and we ask whether a line intersects any of the arcs. In this case, we can actually reduce the preprocessing and storage cost to n to the 1 plus epsilon. Okay, so I'm not going to show this machinery, only mention that we use a couple of tricks. Among them is multi-level RAND searching and the tool from algebraic geometry, the so-called quantifier elimination. They are all hidden there. Okay.
Question, Esther.
Yes.
When you have a line on the partitioning polynomial, the surface itself is very special, right?
Right.
So cannot you use this fact to simplify the queries?
It might be the case, but eventually it doesn't really matter. It doesn't affect the overall bound because the overall bound is n to the 3/2 for the storage and n to the 1/2 for the query. So we might, yeah, I actually, it crossed my mind, but this, I mean, on the other hand, what we show here is a completely independent machinery, which might be also useful for other problems.
Or more complicated problems, potentially.
Right, yeah, I agree. Yeah. But it could be the case.
Okay.
Yes. Okay, so now let us put all these bounds together and show the analysis of the storage complexity. So Sn, that's the maximum storage complexity used by our data structure for n triangles. S0n is the maximum storage complexity for n white triangles in a cell. And S1n is the maximum storage complexity for intersection arcs on the 0 set. Okay, so like I explained before, the complexity, the bounds on S0n and S1n are n to the 3/2 plus epsilon. And therefore, Sn obeys the following recurrence. We stop when the number of triangles in a cell is less than some constant that depends on d, but this is what we get. So we get order of d cubed S0n because this is the handling of the white triangles in each of the d cubed cells, plus the handling on the 0 set, plus the recursion over the narrow triangle. So because those triangles we process in recursion, we have d cube cells, and the number of narrow triangles in a cell is only n over d square. Okay, so this is the good ratio I referred to before. And if we use induction on n, if you feel comfortable with recursive equations, then you get a solution of n to the 3½ plus epsilon for any epsilon greater than 0. So this is the storage complexity. And now let us handle the ray, the query ray. And let us assume, so here I assume that the ray does not lie on the 0 set. If it does lie on the 0 set, the previous machinery already handles that. All right, so we need first to locate the cell tau that contains the starting point Q of the ray query row. And this can be done overall in order of 1 time if d is constant, so I am not given the details. It's pretty standard. The next thing to do is to find all the points of intersection of row and the 0 set. So there are at most OD such points of intersection. We call this parameter T. And then we sort them from left to right along the ray. Okay, P1, P2, PT, these are the points. For technical reason, we also need to take a bounding box for the triangles, but this is not very important for this representation. And then the sequence of intersection points of the ray row with the 0 set ZF partitions row into a sequence of segments, P1, P2, P2, P3, and so on. So I'm going to denote by tau I the cell that contains the I segment EI. And we are going to apply segment shooting within each of these cells in turn. Okay, so this is actually fairly standard. What we do here, we take each of these segments EI, and we perform a ray shooting query in the structure of the white triangle. So this is the, I stated the main theorem about white triangles before, so let's just use it as a black box. So this takes n to the 1½ plus epsilon time and n to the 3½ plus epsilon space. Then we query EI in the recursive structure for the narrow triangles. And then we collect the better answer, the point that is closer to PI, if there is such a point. If there is no such a point, then we proceed to the next segment, EI plus 1. So we make a sequential search over all these pieces. And if we fail at the very end, that we report that row does not hit any triangle of T. Okay, so that's this is the procedure, and let us show the running time analysis. So Qn is the maximum query time for n triangles. Q0 is the maximum query time for n white triangles in a cell, and Q1 is the maximum query time for n intersection arcs. Okay, so again, from the previous statements that I made, Q0 and Q1 are n to the 1½ plus epsilon. So Qn obeys this recurrence. It is the maximum of handling the 0 set, which is done just once and that's it, or going through the recursion, which is handling the white triangles in each of the order of these cells that the ray meets, plus handling the narrow triangles in recursion. So again, every ray meets only D cells. So this is order of D times Q of n over D square. And again, if you use induction on n, the solution would be n to the 1½ plus epsilon. Okay, so this is the query time. Good. Okay. And now, in the time that I've left, I will show you some general description about how to handle the white triangles. This was super technical, but I will try to convey some of the main ideas. So like I said, W is a set of white triangles inside the cell tau. And in general, we cannot replace them by planes. This is the picture. but we still want to do it, say, in an indirect way. That is, we want to do some preparation. And what is this preparation? We are going to apply a second recursive partitioning within tau, meaning that we actually partition the boundary of tau into pseudo-trapezoids. So how exactly we do this partition, it's not very important right now, but we get such a partitioning. And this is actually a two-dimensional cross-section of tau and this partitioning. And let us consider a pair of such trapezoid, of such pseudo-trapezoids, sigma and sigma prime. So these are the two cross-section, two-dimensional cross-section of sigma and sigma prime. And then you're going to take the set S sigma sigma prime of all the segments that start at sigma and end at sigma prime. This is a continuous set of segments, and we are going to consider them now because of the fact that sigma is only, it has a bounded complexity. I'm sorry, let me just check whether something is missing here. Okay, I think it's okay. So we decompose S sigma sigma prime into connected components. Now, since sigma and sigma prime and tau has constant complexity because the degree D is a constant, the set S sigma sigma prime, the set of all those segments going from one cell to another, also has a constant complexity. It has a constant number of components in particular. So we fix such a connected component. This is an algebraic set, but I hope at least you can follow the general idea. So we fix such a component C of the set S sigma sigma prime. Okay, so it represents a subset of those segments going from sigma to sigma prime. And we denote by T of C the set of all Y triangles that are crossed by the segment E in this picture in S sigma sigma prime, and does not cross sigma or sigma prime. What does it mean? I fix such a connected component. I take one arbitrary point, one segment E, and I consider all the all the triangles that it meets. These are the black triangles, and I exclude all those triangles that these are the pink triangles that meet one of sigma or sigma prime. So basically, I look at this set. And what we are claiming is that this is actually a canonical set. This set is fixed. Okay, it is not changing. So what we claim is that TC, the set, depends only on the connected component C and not on E, meaning that if we change E a little bit, it still goes from sigma and sigma prime. And again, we exclude all the triangles that meet either sigma or sigma prime and leave only those triangles in between, then it is going to be the same set. If the query segment belongs to C, then we can actually replace the triangles of TC by planes, because locally this is the behavior. So at last we get this reduction to planes. It's just that we have...
May I interrupt for a second?
Yes.
Just to clarify, these segments that you're talking about, the ones that go from sigma to sigma prime, are you requiring that these segments are completely contained in the cell?
Yes, yes, they should be contained in the cell.
Between the two endpoints, right?
Yes.
They cannot leave and re-enter the cell.
Yeah, otherwise this claim would not be true.
Okay, thank you.
Yeah, sure. Okay, so so this is the base to handle those segments recursively, because we take those trapezoidal cells, and we refine the partition, and so we handle a subset of them in one step and the other subset in the following steps. Again, I am not getting into these details, but if someone is interested after this talk, I can explain that. And that's it. And we show that this mechanism with all the hidden detail gives the performance bound that we want. Okay, so this gives some ideas about how to obtain the bounds for white triangles. Okay, so this is more or less my talk, and I think the time is also good, but if you have questions, I am available to answer.
Thank you, Esther. Please ask questions. Anybody questions? Mattia.
I'm wondering if there is any connection between the work on eliminating cycles in the depth order and using the polynomial partitioning technique and the cutting and the more traditional cutting partitioning. And what you're doing. So you are also like you're replacing an old result which was done using cuttings, etc. With this more with the new, not so new already, with the new machinery.
Right.
So on some level, is there any connection? I just don't know.
The connection is mainly through the tools. I mean, I don't know if through one problem, the solution of one problem can give you the solution of the other, but the divide and conquer machinery is similar. You divide the triangles according to their edges, and you get the right relation between number of edges and number of triangles. So saying that there is a connection beyond it, I mean, the questions of ray shooting and hidden surface removal, for example, they are kind of related. So in papers from the 90s, and Danny, I think you are signed on one of these papers. I think
you cited it.
Yeah, I cited it, but I didn't explain it. I didn't describe it. So there are connections, but currently on the spot, I don't think I can say much beyond it.
Okay. More questions? So I want one more question. It might be stupid, but still. In some of your applications, suppose you know all the cells crossed by what you call narrow triangles.
Yes.
I think that in certain applications, you're only interested in white triangles that are crossing cells that are crossed by narrow triangles, not all crossings of white triangles. For example, for detecting all the intersection between triangles, if someone only told you what are the narrow cells, then you are only worried about white triangles crossing those narrow cells. Because only the answers could lie.
What do you mean by narrow cell? You mean a cell that meets narrow
if you
triangles?
Know that is a cell that is crossed by an edge of a triangle. You're actually only interested in those cells. You still want to cross them with the white triangles, but you're only interested in them. And the question, perhaps, this could be made more efficient.
So the number, okay, so you know that the overall number of, say, interaction incidences between those cells and the narrow is d cubed times n over d squared, which is n times d. So yeah, so if d is constant, this is still all the cells, but I guess when you recurse, when you go down in the recursion, then the cells become more and more scarce. Is that what you mean?
I'm asking, if I told you that you are only interested in those cells, and not in every other cell, namely, if a cell only contains white triangle, it seems irrelevant to yours. Some applications,
yes.
The question is there any saving because you discard such cells?
Well, I think that in general, there is not much saving because the number of the cells is d times n. And the degree d, it should not exceed root of n.
Okay.
Because if it exceeds root of n, then there are theorems in algebraic geometry that say that all the lines lie on the zero set. So it is not very meaningful. And then what you get is that, so d cubed, the number of cells will be always smaller than n times d, which is the subset of the cells that you are interested. Then at least in this aspect, I don't see the saving.
Okay. More questions? So let's first thank Esther again.
Okay, thank you.
Thank you.
Thank you, Esther. And let me just advertise next week's talk, which is the last talk for this round of the seminar. Let me share the new screen. Okay. Do you see the announcement? It's a talk by Alex Steiger from Duke University, decomposing the complement of the union of cubes. I wish you all a happy, healthy new year, and see you next week for the last round of this seminar.
Okay, thank you.
Bye-bye. Thank you,
Bye-bye.
Esther.
Bye-bye.